Great. Hi, I'm Joseph Antony. I'm from the NCI, which is the National Computational Infrastructure. We're based in Canberra, and I'll be talking about our use of Lustre along with my colleague Patrick Fitzhenry, who's the engineer on site. The agenda for today, we're going to quickly cover what the NCI is, what we do nationally in Australia. We'll talk about the petascale machine that we use, and we use Lustre as a root file system, so sort of touch on that and show you some preliminary numbers we have for booting up nodes directly over IB. We'll then cover Lustre as it's used on the peak system, as well as site-wide Lustre and our future plans, which involves complex workflows with Lustre. So who are we? We've been funded by the Australian federal government and research-intensive universities and various government bodies, and our mission is to provide the computational infrastructure to foster ambitious and aspirational research objectives using high-end computing. So we're driven by research objectives, and the idea is to set up a vertically integrated research service. So this is usually done on a merit-based process, and it's done as a national scheme. And the way this works is typically you'd like to get Nature papers coming out on the top. And what we typically do is we work with end-user communities. So this is in climate science, astrophysics, the space department in Australia, people who work in satellite image processing, for example. And we have an interaction with them, which then results in either virtual laboratories, which essentially encapsulate workflows, or it could be all the way down to, oh, you want SSH access to a system right now. And the key thing here is, from this, we essentially derive requirements, which ultimately then decide hardware choices, what we do on the peak system, etc. So it's very top-down, and it's typically driven by needs like we'd like to get certain climate simulations sorted out by, in a certain amount of time. We have emergency computing for land and water use, for example. Now, if you're wondering where we are, we're located in the nation's capital, and we're housed at the National University. So we're south of Sydney. It's about 3 hours drive. I'll move on to talking about the research communities that we engage with. So what this slide is talking about is essentially the workloads that Lustre ultimately sees. And we have a gamut of users. So they range from climate science and earth systems science. So this is classical climate models, looking at sea ice, etc., all the way down to astronomy. We're working with Brian Schmidt, who won the Nobel Prize in Physics recently, and this is for a large project called SkyMapper, where there's an automated sky survey. It requires processing of data sets on the peak machine as well as within virtual machine environments. We have users in the geosciences area, lots of satellite image processing, bioinformaticians, and we do Twitter analysis with, for social sciences. So there's a wide gamut of users here, and it's not just one application alone. So of late, a growing emphasis has been on facilitating cloud services, and we participate in something called the Earth Systems Grid for managing climate data. One of the other things that's happening down under is a $100 million government initiative known as RDSI and Nectar. So essentially, the government is seeding money for storage around the country, and the setup of a national academic cloud called Nectar. And in previous slides, I talked about virtual labs. So these guys are funding virtual labs in weather, all sky observatories, and material characterization. So essentially, here it's the process that we need to go through is how do we create a seamless research environment for various groups, and how to do this successfully. Finally, One of the other use cases is visualization. We've had the VisLab essentially using facilities, and we write code for display walls, visualization software, and other areas. I'll move over to some of the one of the key priority science areas that we have, and it's really on enabling a national climate modeling capability. So what's interesting in Australia is when you see the weather forecasts daily, it's using the same code base that's used in the research side. So this is a big effort which is led by the Bureau of Meteorology, CSIRO, and us being in there. So a key goal here was how could we enhance the value of this particular code base, which is called Access. It's derived from the UK Met Office's model. And how do you essentially create this environment which would allow people who are coming in from operational weather forecasts to run longer decadal forecasts? So the key requirements were you need to provide high-performance computing, but critically, you need to store these simulations, have a data repository, and as well as a cloud capability for data processing, analysis, and visualization. So what I thought was, I'll show you a video from one of our end users, and just a quick snapshot of his work.
My name's Dr. Andy Hogg. I work at the Australian National University, and I'm a member of the ARC Centre of Excellence for Climate System Science. I work on the role of the ocean in climate change because it traps a lot of the heat associated with global warming, and it also absorbs a lot of the carbon dioxide that humans emit. There's a lot of processes going on in the ocean which are very difficult to observe because the ocean's so large. We have a good understanding of how they work physically, which means that we can model them on a computer and try and understand them better that way. The problem is that because they depend on very small scales and the ocean is very large, it's a very large computation to make. We're now integrating models that are perhaps 10 times more resolutions than we had 2 years ago. And what that allows us to do is it allows us to understand the vertical transport of nutrients which create phytoplankton blooms in particular regions of the Southern Ocean. When I started this work about a decade ago, I was running on a machine where I'd use 8 processors at once. At this facility we have over 57,000 processors all hooked up together. We can currently use about 3,000 or 4,000 of them on one program. It allows us to run ocean models which include more and more physical processes, and that allows us to get an understanding of the climate system and in particular roles of small-scale processes that we couldn't do previously. Our work is really, I think, underpinning the improvements in climate models that we'll see in the next 5 years.
Essentially, a key part of the work that Andy's doing is driven by Lustre and how well we can get Lustre working. So from this, I'll switch over to some of the current infrastructure that we have and how we're using Lustre in production. So since 2000, we've typically had a system that's been in the top 30. And our current system is a Fujitsu x86 machine, debuted at number 24. It's called Rygen. What is Rygen? Essentially, a big fat tree network, FDR InfiniBand, which links it all together. We have a Lustre file system provided with DDN hardware at the back end. We're getting about 150 gigabytes per second. The largest codes that we run are typically on the order of about 40,000 cores. And the usual work mix is about 1,000 cores. In terms of storage, there's a big HSM system that we have. It's based on DMF. We're moving to a site-wide Lustre file system. We've also been playing with Ceph. Right now, it's being used on our cloud node, but we're considering its long-term use when Erasure coding matures for its back end. We've got cloud infrastructures, we have VMware for mission-critical applications, and our new OpenStack-based cloud node goes live, so it's got a particular emphasis on data-intensive work, so it's got 160 terabytes of SSD, 56 gigabit Ethernet with Rocky. One of the people in my group are looking at potentially getting Rocky working over LNet, so we can get access to our Lustre file systems on site. So finally, to give you some context, these are the two main areas that we'll be talking about today. There's Rygen, which is the peak system and its Lustre file system. And we have what we call GData, which is this site-wide Lustre file system. And with that, I'll transition over to root over Lustre. What is root over Lustre? So typically at our site, we have the root file system being provided by Lustre. And we use OneSys for provisioning with some minor patches. Why do we go down this route? Simplicity. It's a lot of ease of management. All of our nodes are diskless. We have one golden image for multiple compute clusters. Yum update on the golden image is instantaneous. It's synchronous because once an update is made on the root file system, all of the nodes see it. And from a security perspective, this allows us to carry out coherent patching because it's not about the OS on individual images, for example, individual nodes. And we've been using this in production since 2008. This was work done by a colleague of mine, Robin Humble. He's documented this, and effectively what happens is there's just a kernel line parameter which tells OneSys where to go and get its boot image from. I'll present some boot times right now. So we've been using Flexboot over IB, so this allows us to essentially boot over nodes, boot nodes over InfiniBand. So the idea here is Lustre's a scalable backend. We have a scalable interconnect. And we had some initial bugs with Flexboot, but it's working fine. And typically what we found is it's almost linear, whether we go one node, a chassis, or one rack. So we're planning to put this into production very soon. So with that, I'll hand over to Patrick, who's going to talk about Lustre on Rygen.
Good morning. I'm going to talk about the Lustre file systems we've got on the petascale machine at NCI. So all the storage for the Lustre is built up from storage blocks of DDN 12Ks. There are 5 storage building blocks for the file systems, and each building block has 70 RAID 6 pools, which is for the scratch file system, 20 RAID 1 pools, which are on 7.2K SAS, which are for the home file systems, and another file system called System, and 40 RAID 1 pools, which are on 10K SAS, which are for the images, which serve out the images to the compute nodes, and for the apps, which contain all of the general software applications. We also maintain some hot spares for the RAID 1 pools. So one of the main one of the main features for NCI is that Lustre is so important that if it goes down, the entire system is completely down. You can't have any compute nodes. So redundancy is really important to them, and data integrity. Hence all the RAID 1 pools, and also hence all of the fully redundant cabling. So this slide is just basically showing that everything is fully redundant on the storage side. And similarly for the metadata storage. For metadata storage we use 15K SAS RAID 1. It's hardware RAID 1, then they have software RAID 1, and they have LVM on top of that, so they can take snapshots of their metadata targets. And the metadata storage is built up of building blocks of these EF3015s with expansion chambers. So the scratch file system has 4 of these. The other file systems have 2 each. So there are 6 metadata servers in 3 HA pairs. One of these pairs is active-passive, and that's just for the scratch file system. The other 2 pairs are sort of active-active for different file systems. And there are 50 OSSs organised into 25 HA pairs. All the Lustre servers themselves are diskless as well. So currently we're running CentOS 6.3, and we just a couple of weeks ago upgraded to Mellanox 2 and Lustre 2.16 with Coruscant pacemaker. So this took us about 3 hours to get an image going, and then it was just a case of rebooting all of the servers and remounting Lustre. As I said, there's 5 file systems. The scratch file system, the images for the compute nodes, the user applications, home directories, and system is underutilized at the minute. So when we were installing Lustre at NCI, they had the requirement that all metadata storage had to exist as LVMs on top of software array 1, on top of hardware array 1, so they have this four-way mirror. The acceptance requirements were all based just around the Scratch file system. When we originally went in, DDM was just going to commission the Scratch file system, but due to some other problems, they asked us to commission other file systems later on. So the initial acceptance testing requirements were 120 gigabytes a second for sustained streaming write performance. So we achieved 143, but we've done some recent reconfigurations. We've managed to push that up to 152. Random I/O performance, they wanted to see 7.5 gigabytes a second. We managed to achieve 75. And creation, stat, and delete of 64K files in a shared directory. They wanted that done in 53 seconds, and we were able to get it done in 12 and a half. So the final slide I've got really is just to show you the sequential performance. This was performed in December last year when we were doing the initial acceptance testing. This graph's courtesy of Suichi Ihara from DDN in Japan. And you can see here that at that time we had 400 OSTs for the Scratch file system, so that you can see that once we got up to the peak bandwidth, we managed to sustain it for up to 4 times the number of processors. And finally, this is just a summary of the systems. I'll just draw your attention to the performance. So the images and apps are actually read-only file systems, and the sequential IOR write performance results are only there to be indicative of what the read performance should be. We currently have an outstanding issue with Fujitsu concerning the read performance, which is being investigated. That's it.
So I'll now talk about the site-wide Lustre file system that we have. And essentially, the motivation here was we needed to avoid moving data between multiple clusters, multiple storage pools. Plus, we were getting complex environments where you'd have simulations running on the peak machine. You might have a Windows VM with some bespoke software, or a bit of software that comes from an Ubuntu VM, etc., because of the community it comes from. And the big issue was, how do we make all of this work? So 2 things had to be addressed. One, how do we manage to handle technology transitions? How do we manage to handle multiple vendors? And then how do we get onto the clients that will ultimately use these file systems? So currently, what we have is a system that we call GData, and essentially, it's got management servers, NFS servers, LNet routers, about 60 OSSs, and we've got a mixture of SGI/NetApp arrays and some DDN arrays. So this file system that we have on the NetApp/SGI arrays are what's called GData 1, and it's running Intel Enterprise Lustre. So the key emphasis here was data has to be resilient. We want to have enterprise support. Essentially, users should know that there's back-end processes so that we can actually handle bugs, escalate it, etc., in a timely manner. So this is running IEL, and this is called GData 1, and this is all arrays from a particular vendor, and then we have performance expectations, quite modest without LNet routers, 48 gigabytes per second read, 43 gigabytes per second write. But we're going to throttle it down purposely by using about 13 LNet routers to Rygen, so that people will purposely use the short Scratch file system on Rygen and only move data out for long-term archival purposes, because policing users is a hard problem. So we're purposely going to throttle them. The next generation of GData is going to be built on SFA12Ks, and this is called GData 2. It also runs Intel Enterprise Lustre. So to sort of summarize, I guess we use We've bet the farm on Lustre. We use Lustre on our peak systems. We use Lustre for our site-wide capabilities. It's used as a means to tie together our investments in HPC, cloud, and visualization together. We have complex workflows which happen a lot of the time post-simulation. Data also needs to be disseminated, and the idea is this will use our OpenStack infrastructure, and this requires access to Lustre. So in a sense, one of the key reasons why I'm keen about LADs is I'd like to find out what's happening with Lustre HSM, Lustre WAN, Lustre Kerberos, because we have users pounding on our door and asking us for these features right now. HSM to actually manage multiple copies of data on tape, for example. Lustre WAN, primarily because Nectar, which I mentioned was this academic cloud, will be running across the country, and we may have instances where the data is located over in Canberra, but you get virtual machine cycles over in Queensland, and you would need to mount this across 40 gigabit and potentially now 100 gigabit Ethernet backbone, which is going in. So how do we do that? And we'll be interested in looking at the Kerberos feature sets also. This is around securely accessing Lustre. So with that, I conclude, and like to ask, open the floor for questions.